Okay, so here's where we already start seeing some problems with valence bond. And if you look at the orbital diagram for carbon and you look at the number of unpaired electrons, what you see is two unpaired electrons and then a pair of electrons in the s orbital. So how many bonds would you expect carbon to make? Well, if it's based on the unpaired electrons, then you could only make two bonds. And these would be 90 degrees to each other. So a couple of observations, right, for carbon. Two bonds, 90-degree bond angles. If you actually look at carbon bonding to hydrogen, it actually normally makes four bonds, and the four bonds have a 109.5-degree bond angle. So you have to think about the discrepancy here. You could see how you could get four. That is, if you took this electron and you promoted it out to here, that's the term. Because you have to remember, the 2p orbital is slightly higher in energy than the 2s. So you would have to promote it or put it to a higher energy level. And then you could form the four bonds because there would be four unpaired electrons. On the other hand, even though you do that, that doesn't explain the 109.5-degree bond angle. So one of the things that had to come about was that people had to look at the orbital wave functions and think to themselves, how do these things combine, or how could they combine to give this kind of bond angle? In fact, there's three bond angles with carbon that we have to be concerned about. One is the 109.5, that's for tetrahedral. But carbon also makes, for example, when it's double bonded with two single bonds, can also make a 120-degree bond angle. And if it has a triple bond on one side, or a double bond on each side, it's a 180-degree bond angle. And really, none of these make any sense according to atomic orbitals and quantum mechanics. And so something else had to be missing in our understanding of how this process was taking place. And that understanding came with the looking at the wave functions and deciding how they could recombine in order to produce a new set of wave functions, which means a new set of orbitals. And I'll show you that process actually for something like this situation over here. So some of what I'm going to say here is actually formalized later, but I wanted to show you how you can mix s and p orbitals from a single atom. So let's start with drawing s and p orbitals. So an s orbital is going to look something like this. This is going to be psi 2s, but I'm actually going to ignore, if you remember, there's a radial node in here. I'm just going to ignore it and give the general shape for what the wave function looks like. And I'm going to use blue because blue is generally what we use to represent positive values. So the wave function is positive. And then I'm going to draw the same for the 2p orbital. So for the 2p orbital, I have an axis that looks like this. And then what happens is it has a negative side, and it also has a positive side. So it's like this. Now, remember, this is psi for 2s. Remember, these are both on the same atom. This represents the nucleus. And so what valence bond theory did was said, well, if these are both on the same nucleus, I can create a new set of orbitals from it by allowing there to be both constructive and destructive interference. So I can superimpose this wave function onto this wave function and look to see what the result looks like if I allow for constructive and destructive interference. So I'm going to draw the 2p on top of this. Okay, and then I'm going to draw both lobes. So remember, one's positive, one's negative, and the 2p is going to be about the same size. So that's why I'm trying to match them up. And it shouldn't like drop all the way to the axis. It just sort of asymptotically goes towards zero on both sides. But anyways, what's going to happen when I add these two functions together? Well, these are positive values on this side, and this is a positive value up here, but a negative value that I'm adding on top of it. So what ends up happening in the orbital when I allow an S and a P to mix, this is the term mixing, it's just really adding the two orbitals together. What ends up happening is I get a wave function that looks like this. The positive parts are going to add. They'll actually be bigger. And then on the negative side, it's going to be like this. And it becomes asymmetric. And it has a large positive region on this side and a large negative region on this side. Now, it doesn't matter that it's positive or negative, but what does matter is that I'm going to have a high electron density on this side and a low electron density on this side. And if I were to take this and convert it into an orbital image using a probability density map, what I would end up with is something that looks like this. Draw my axis. I'm drawing it asymmetric because the orbital will be asymmetric. This side would be bigger. That's supposed to be three-dimensional. And the other side will be smaller, like this. So I get this shape, which is known as the hybrid orbital shape. It's got a large lobe on one side. This is the bonding lobe. Because remember, in valence bond theory, one of the premises is that when you form the bond, the better the overlap, right? The stronger the bond, or the more stable the bond will be. So I can create a bonding lobe that's large on one side. Now this is not the bonding lobe, but this is the bonding lobe, and this is the side that it's going to attach to another orbital from another atom. Now, this is for constructive interference. What if I make it destructive interference, right? Destructive interference is going to do something opposite of that. What will happen is I'll subtract this side from this side, okay? And then that means this will be positive and this will be negative. So doing the subtraction really just means adding the opposite. So really what I'll do is I'll multiply this times -1. And so it's going to be poking down here, and this one will be poking up here, okay? So when I do that, what ends up happening is I get another orbital that forms, and that one's going to be pointing out like this. And this little bit will be hidden in there, and then on the back side of that same orbital, I'll have this. And this will be, right, basically this will be the mirror image of this orbital, although I didn't draw it very well, but it's the mirror image of that orbital. So what ends up happening when I mix an S and a P orbital is I get two orbitals that are 180 degrees apart from each other. This bond angle will be defined as 180 degrees, right, by the angle that's created between these two orbitals. So what does that, why does the 180 sound familiar? That's exactly what's going on when we're talking about this situation. This is going to reflect the sp hybridization of the carbon atom, where it can direct one bond to the left and one bond to the right. Now you're looking at this and it's a little confusing because there's 3 bonds in here, and we'll explain that when we get to this particular bonding scheme, okay? But again, mixing of S and P orbitals, this is what we call hybridization. And really what we're allowing to happen is we're allowing the atomic orbitals on a single atom to interact both constructively and destructively. And when that happens, what we end up with is 2 new orbitals that are coming from 2 orbitals. So this is kind of a summary of the main concepts. So we have atomic orbitals that we're going to hybridize. And when we form hybrid orbitals, right, we have orbital conservation. That is, for every orbital that you put in, you get one hybridized orbital out. So if I put in an S and a P, I'll end up with two sp hybridized orbitals. The way we determine the hybridization in valence bond theory is by looking at the Lewis structure, okay? And we look at the number of electron groups on the central atom. So electron groups determines the number of orbitals we use, because that's going to be determining how many things we can bond and how many lone pairs we'll have on the central atom. We typically combine the same set of orbitals together when we do hybridizations. And so what a lot of people will do is write this out. S, P, 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 D, D. And we're actually, you could add other D orbitals here, but if you remember, there's one S orbital in any subshell. There's 3 P's, and then there's 5 D orbitals over here. Typically, we're not looking at the ones that are out here. There's 3, ooh, that's supposed to be pen. Let's do this. We're not looking at these other ones. We're just looking at these. And the reason we're only looking at this many is because for the most part what we're looking at is up to 6 groups around a central atom. So if we had a trigonal bipyramid looks like this, for example. I have 5 groups on the central atom, then I would take 5 atomic orbitals and hybridize those together. Now, that atomic orbital will be called sp3d because I'm using an S, 3 P's, and a D. And again, the number of orbitals is determined by the number of groups. Okay, so if I had XEF2. Oh gosh, I keep tapping all these things on the screen accidentally. I decided to draw it and let the computer deal with all of its little menu changes it's trying to keep pulling on me right now. So here's XEF2. We have xenon in the middle, right? And then we have 1, 2, 3, 4, 5 electron groups. So even though this is a linear molecule, it has 5 electron groups. Both of these fall under the sp3d hybridization. Now, if we did XEF4, then I have, and I left the lone pairs off the floorings, but they all have octets. If I do XEF4, then I have 1, 2, 3, 4, 5, 6 groups. And this would be sp3, and then I have to use 6 groups, so it's 1, 2, 3, 4, 5, 6, sp3d2, because I have to use both of those d orbitals. Now, I did show an example earlier where there were actually 7 groups, and if you did the hybridization scheme for 7 groups, you would have to include one of these orbitals that's not used in your book when they do these kinds of things. But you can have more orbitals involved in the hybridization, but the standard is to go up to 6 groups. Okay, so a couple of things about the hybridization. Hybridization will occur when you can have better orbital overlap. That is, you can, and this happens when you can spread the groups out. So we're getting less repulsion, right, by spreading groups out to better angles. So that's one of the reasons why hybridization will take place. The other one, and probably the most important one really, is that you can make more bonds. Because every time you form a bond, if you remember our discussion from before, when we're talking about bond energies, right? Breaking bonds is endothermic, but making bonds is exothermic and leads to the release of energy, and the molecules, when they have more bonds, will be more stable. So typically, if you can hybridize and make more bonds, then that's a situation where it'll happen as well.